Welcome back. Let's look at our first example for potential energy. And for this problem, I didn't have a picture drawn because I figured it'd be a good idea for us to draw it out. So here, let's go ahead and draw out what we've got, and then we'll go over the actual statement. So we're going to have a rod. It looks like that. And it's in between two fixed points here. And we're going to have a slider on here. Make it a different color. Alright, so here is our slider. Now, attached to this slider is going to be a spring. Alright, and the spring is going to be attached up here. So initially we're going to have a spring. It's attached right here in the center. And it's like that. Alright, so we've got that there, and this is point A. And what it's going to do is it's going to start at rest at A, and then this spring is going to cause this little slider to slide up to this point up here at B. All right. Now, when it's at B, the spring, obviously, let's make this a little bit bigger. The spring is going to have changed lengths, right? So it will have shortened to get up here. Now this distance from A to B is going to be 18 inches. And then the distance from A to B right here, that's 10 inches. And then finally from this point up to where the spring is connected, that is 20 inches. Obviously that's not to scale. You guys know by now that I'm not very good at drawing pictures. So this spring here is supposed to be vertical, by the way. So that's what we've got. Alright. And B is right here where the slider ends up. Alright, so now let's read this problem. So the slider weighs 2 pounds, initially at rest at A, so that's important. And the spring causes the, whoops, this should be slider, typo. So it causes the slider to slide up the rod until it reaches point B. Now the spring constant is given, so it's 1.6 pounds per foot. And we are also told the spring's unstretched length. So that length is 15 inches. We want to know the speed at B. So the speed with the slider gets right here. Okay, and then this spring should be vertical. Now, what we're going to do is we're going to use our work energy balance equation we just came up with. All right, and that was this one right here. All right, so now we got that. And I know that I can use this. This is a good choice for this problem. Instead of looking at like force and acceleration, this is a good one because all I care about this starting point, I care about the end point, right? I don't care about how we get there. I just want the end points, all right? So there's no real need to use the methods from that previous section. All right, so now that we have that, we're going to find each of these 3 things, and then we'll see if we can find the speed at B. All right, so let's start with delta T. So delta T is going to be the change in kinetic energy. So that's the 1/2 m times v, let's see, this will be VB squared minus VA squared. All right, so we've got a value for VA, and we can find the mass, so let's put that in there. That'll give us 1/2 times 2. This weight was given, so we need to divide by 32.2 and then multiply by VB squared minus 0 because we were initially at rest here. Now we get that. Simplify that, we get VB squared over 32.2. Now let's do delta VG. Now when you're doing this one right here, you're going to have to come up with a reference point. And you're going to measure your heights from that same point for the whole problem. All right, so I'm going to make this right here be my reference point. All right, so this lines up where we're starting at right here at A. All right, so those are lined up. So I'm going to measure everything from that line. Okay, so now with that, remember this equation is mg times delta H. All right. So now mg, well, that's weight, right? Weight was given right here. So I'm going to have 2. And then I need to worry about my delta H. Now before we go any further, these are all in inches. Let's go ahead and convert those to feet. So that one right there is 1.5. The 10 inches will be 0.833 feet. 20 inches is going to be 1.67 feet. Okay, and now for the delta H, we're going to have H2 minus H1. So H2 will be this point here at B. So that's going to be 0.833. And then we'll subtract the initial height. Well, the initial height, if I'm measuring from right here, what's that going to be? 0, right? So now we got that. And that's going to give us 1.666 foot-pounds. Okay, so now we're done with that. Now let's do the spring. Actually, let me move this down here. We need more room for this one. Now for the elastic potential energy, let's write down our equation. We're going to have 1/2 times k, and then you got your final x. So for us, that'll be xb squared. Subtract the initial x, so we'll have xa squared. Now remember, this is the stretch or the compression in the spring. Keep that in mind. So now let's fill in what we know. We're going to have 1/2. K was given, 1.6. Plug that in. And then we got to find our x values. All right, so let's do xb first. Now remember, it's stretch or compression. So my unstretched length was 15 inches. All right, now when I'm at B, how long is that spring? Well, that spring is 20 inches. Okay, so basically we need to do the difference here. And by the way, 15 inches is 1.25 feet. All right, so we're going to have 1.67, because that's this length right now, minus the unstretched length. Okay, so that tells us how much the spring is stretched. And then we're going to square it. Okay, so that's the first one. Now, the second one that we need is the initial amount of stretch or compression. Well, now for this one, the spring is over here. All right, so it's looking a little longer, right? So for this one, what I need to do is I need to find this length, and then I'm going to subtract the 1.25. So this length right here, we can get that basically using a right triangle. All right, so we're going to have the square root of this length right here, so 1.67 plus 0.833, square that, and then we'll have plus the square of the 1.5. All right, so basically we use that right triangle. All right, so we had that, and then that right there, and I'm wanting to find this value here. Okay, so that gives us the length of the spring at A, and then I want to subtract the unstretched length. All right, so subtract the 1.25 and then close that parentheses, square that, and then close the bracket. All right, now that we've got that, you can do all of the math, simplify that, and you're going to get negative 2.08 foot-pounds. All right. right, so now we have that. Now the last thing you need to do, we've got everything on the right side done. You need to look at U. Remember, U is work. And we said U was going to take care of any external forces other than gravity or springs. Now, do I have any other external forces? No, right? I don't have anything. So this is going to be 0. And that's because there are no external forces. We just have gravity and then the springs. That's all we got. So now the left-hand side is going to go to 0. And then we're going to set that equal to VB squared over 32.2 plus 1.666 minus 2.08. And then with that, you got your one unknown, so you can solve for VB. And you get 3.65 feet per second. All right, guys, so that's how you go about doing that problem there. All right. So we'll stop that one here and we'll pick it up in the next video with another example. See y'all then.